Sounds good.
Okay, good day, everyone. Here we have Lem Hui from Columbia University, who will tell us about dark matter waves.
Thank you, Dima. Thank you, everybody. Thanks to the organizers. I want to talk about the subject of fuzzy dark matter specifically, but more generally about actually dark matter as some sort of waves, as you will see. And it's based on work done with a number of collaborators. I listed them here. The main subject of the talk has to do with vortices, which is described in the very last paper on the slide. And the collaborators there were Austin Joyce, Michael Landry, and Xinyu Li. But let me start with some general introduction, which is more based on the first paper, which is collaboration with Jerry Oestreicher, Scott Tremaine, and Edward Witten. So some very general comments that I probably do not need to make for this audience. There's of course a lot of rich evidence for dark matter, largely from its gravitational effects. So I'm going to just skip these bullet points because they are very familiar to most of you. We know dark matter exists based on an abundance of evidence. We have very little idea about what it is. One sign of our ignorance is that we don't even know the mass of the dark matter particle if it were a particle of some sort. And this slide kind of illustrate the wide range of possible masses that people have considered in the literature. We do know one thing though. We do know the dark matter density, mass density, for example, in the solar neighborhood, based on dynamical measurements. And based on that one number, at least there is a characteristic mass scale that we can put down here. And the mass density is about 0.3 GeV per centimeter cube, as you might know. We can ask a very simple question. At what mass for the dark matter particle, below which the average interparticle distance would be smaller than the de Broglie wavelength? This is the same mass scale that was actually described in Dima's talk earlier. So I put down this little picture. So imagine the dark matter particle was so light that the de Broglie wavelength of each particle, which is described by this brown circle, is larger than the interparticle distance. And it's very easy to work that out. The characteristic mass scale is around 100 electron volts. It's exactly the same scale that Dima described in his talk. And this we would describe as the wave regime. So this is a regime which is described in many different kind of terms, both Einstein condensate, wave dark matter, and so on. And we are interested in this regime, of course, in this conference. In particular, we are interested in the very light masses, 10 to the minus 22. But more generally in this talk, most of what I describe, except maybe at the very beginning, most of what I describe apply to any mass that is less than 100 electron volts. And here I give some examples. The fuzzy dark matter, which is the lowest mass, 10 to the minus 22 electron volt. The de Broglie wavelength would be 100 parsec. Of course, that depends on velocity. So here I use the velocity dispersion of the Milky Way, which is about 200 kilometers per second. Another example, a typical QCD axion mass, of course, the mass has a very large range, but if I pick a fairly common mass, which is 10 to the minus 6 electron volt, the de Broglie wavelength is considerably smaller, is 10 to the 4 centimeter, but it's still pretty big, big in the sense that we are still in the wave regime. An outline of what I want to say in this talk, I will start with some particle physics motivation, which again is probably very familiar to this audience. So I will be very quick in going through that. And then I'll quickly show the same equations that describe the dynamics that Dima showed in his talk. And most of the talk, I will be talking about the astrophysical implications, and especially I'll focus on the subject of vortices. And I'll close with some thoughts on experimental and observational implications. The term fuzzy dark matter was, of course, introduced by this paper that I cited here, Hu, Bakana, and Gruzinov. And of course, there's a very large literature on this subject. So let me start with the particle physics motivation. A very natural candidate for a light particle, a dark matter particle, and in this case, it would be a bosonic particle, that is some kind of a pseudo-Nambu-Goldstone boson. The most well-motivated example is, of course, the QCD axion, which solves the strong CP problem. There are a lot of candidates for axion-like particles. The term axion-like refers to the fact that this is not the QCD axion, but it's axion-like in the sense that it's still some kind of pseudo-Nambu-Goldstone boson. In fact, I put a picture of the Mexican head potential just to remind you. So this is the particle that's associated with going around the Mexican head. If this were a strict Nambu-Goldstone boson, it would be massless, but very often non-perturbative effects would generate a potential, giving a small mass, as if you are taking the Mexican head potential and tilting it just very slightly. There are a lot of axion-like particles in string theory that comes from basically thinking about compactification, higher form fields whose Kaluza-Klein modes can be thought of the axion-like particles. And there is again a subject of a large literature. So the first motivation, if you want, in terms of thinking about a very light dark matter particle, there's of course the classic QCD axion, more generally the axion-like particles. Let me focus a little bit on fuzzy dark matter, which is basically the ultralight regime, 10 to the minus 22 electron volts. There is actually some kind of additional statement one could make, and which is in the next slide, and which comes from basically thinking through the argument from basically the radic abundance from the Big Bang. So the axion particle, can you see my pointer, by the way, Dima? When I move my mouse, can you see the pointer? Okay, great. So phi here is the axion particle, and this kind of potential is fairly standard. Basically, you can think of the axion as some kind of angular field going around this Mexican head potential, for example. And as an angle, it is periodic, and the periodicity scale is called capital F here. It's often called the axion decay constant. It plays the same role as the little f of A that Dima used in his talk. And this potential is typically generated by non-perturbative effects. And you can read off the mass of the axion by just expanding out the cosine. The mass would be of the order of this lambda square over f. Lambda is just this constant in front. And typically, these non-perturbative effects are fairly exponentially suppressed. And so lambda is typically a very small number. F can be as large as the Planck scale. In a lot of this string theory construction is somewhat below Planck scale, something like that scale. Lambda is very small, exponentially suppressed compared to that, and giving you a mass that can be very small. Now, this particular mass, which is 10 to the minus 22 electron volt, often called fuzzy, the fuzzy regime, the fuzzy dark matter, or the ultralight regime, is motivated by thinking about dark matter abundance today. And I'm not going to go through the arguments, but essentially is what in the literature is called the misalignment mechanism, which is to say, you hypothesize that the axion has some non-zero vacuum expectation value in the early universe. And let's say in the absence of additional argument, it's natural to assume is of the same scale as the periodicity scale or the axion decay constant. Let's say that is the primordial value. And for a long time after the Big Bang, it will be just stuck at this value because of Hubble friction until when the Hubble parameter reaches the mass scale of the axion. And then this axion field will start oscillating. And if you go through the argument, it's actually very simple to work out what is the Rayleigh abundance today. The oscillation in the axion get redshifted over time, and fairly quickly, the axion will be oscillating close to the bottom of the potential, which means you can even ignore this cosine altogether. You can just approximate as m squared phi squared. And you can check that the energy in these oscillations redshift just like matter. So this is a good dark matter candidate. And if you work on the numbers, you roughly get the correct abundance if you assume two things. One is that the axion decay constant is of the order of 10 to the 17 GeV, something around Guth scale, somewhat below Planck scale. And the mass of the axion is rather light, it's 10 to the minus 22 electron volts. I should emphasize though that the Rayleigh abundance is clearly more sensitive to what we assume about F than what we assume about M. And so if you just change F a little bit, clearly the required M to match the Rayleigh abundance could be a lot different. So there is actually a fairly wide range for M. So one should keep that in mind, just based on this argument alone. 10 to the minus 22 as a number is not particularly picked out, but something light, something rather light. So this argument suggests maybe we should think about a fairly light dark matter particle. So that's the argument from Rayleigh abundance as one motivation for thinking about fuzzy dark matter. And that's what we are going to explore. Let's just have one summary. Again, this summarize what Dima already talked about. The equations that describe the dynamics. Because our axion oscillations is close to the minimum, we can just ignore the cosine potential or the self-interaction of the axion. And so the dynamics is well described by just the Klein-Gordon equation, where phi is the axion field. And since we are interested in application in the non-relativistic regime, remember typical galaxies like the Milky Way, the velocity dispersion is hundreds of kilometers per second. It's much less than the speed of light. So we are interested in non-relativistic regime. So the standard thing to do is to introduce a complex scalar. The axion phi is a real scalar, psi is a complex scalar, and where we factor out the main oscillation frequency, which is just m. So psi is still time dependent, but its time dependence is much slower than m, and it's fairly easy and standard to derive from the Klein-Gordon equation, the Schrödinger equation. Where psi now looks like basically the wave function that we are familiar with in quantum mechanics that describe, that obeys the Schrödinger equation, with a potential which is the gravitational potential. So I should have written down the other equation, which is the Poisson's equation. The gravitational potential is sourced by density, and the density goes like psi squared. And this is basically the Schrödinger plus Poisson system that Dima also described. And let me just say one word here, and probably is unnecessary to this audience. Despite the fact that we have Schrödinger equation here, this is really a classical system because we have a large occupancy. We have a large number of particles per de Broglie volume. And because of that, this complex scalar psi is best thought of as just a classical scalar. Nonetheless, we'll continue to use the term wave function to describe it because that's familiar. It's also helpful to keep in mind an alternative description of this system. The wave function psi has an amplitude and a phase. The amplitude can be thought of as the square root of density rho. The phase turns out can be thought of as some sort of velocity potential. In other words, you can actually ascribe fluid meanings to this variable. Velocity is the gradient of the phase divided by the mass, in which case it's possible to show that you have mass conservation, which is basically the analog of, in quantum mechanics, you would have called this probability conservation. There is a U1 symmetry governing basically this wave function psi that tells you there's, in the fluid description, there's mass conservation. And of course, because the Schrödinger equation is a complex equation, there should be two independent equations. So the other equation is some sort of Euler equation, where most of the terms are fairly familiar. The left-hand side is just the acceleration of an individual fluid element. The first term on the right-hand side, there is, of course, acceleration from gravity, the gradient of gravitational potential. And then there is this perhaps unfamiliar looking term, which is often in the field called quantum pressure, although it is really, strictly speaking, not pressure. And in our context, it's neither quantum either, because we are talking about a classical system. If you work out actually the stress tensor associated with this fluid, it has off-diagonal terms. So there's actually some sort of stress in it. Although in my talk, I will continue to use the misnomer, I call this quantum pressure from time to time, but it basically takes this form, okay? And that's basically it by way of introduction. And let me skip this slide. And let me actually just play a movie just to emphasize the wave phenomenon, the fact that we have waves here. And I should say, the fact that you have this wave interference feature that you already can see in this simulation. This snapshot of a simulation is basically starting from Gaussian initial condition from basically in the early universe, and you just let it evolve gravitationally by solving the Schrödinger-Poisson system. This kind of wave interference pattern was emphasized first in a very nice paper by Shive, Chiu, and Broadhurst. You will actually hear more about simulation from Shive in the conference, and also probably from Bodo. Let me just play the movie. I don't know whether this would actually work. Let's try it. Can you see the movie? This is actually, by the way, not actually a movie in time, I should say. So all I'm showing you here is one snapshot in time in a three-dimensional box. And I'm just showing you different slices, just to emphasize the three-dimensional structure. And you can clearly see the phenomenon of wave interference. And in particular, what I want to emphasize in this talk is actually the disruptive interference, which is basically these places where the density goes to actually become very low, basically these dark features. And in fact, I want to consider places where the disruptive interference is actually complete. The disruptive interference actually takes the density code all the way to zero, which is rather extreme, but you will see why I want to focus on them in a moment. But let me also emphasize this phenomenon of interference is of course present even in the early universe. But there is something very special about the nonlinear regime. In the early universe, the wave function is mostly homogeneous with a small fluctuation in space. And of course, those waves, they interfere. But because the fluctuation initially was small, you cannot have complete disruptive interference. Any disruptive interference can only lead to small effects. The density can never go all the way to zero. However, once you reach nonlinear regime so that the wave has actually large amplitude, then you have the possibility of having complete disruptive interference. And so that is something that you can only see in the universe.
I have a question, Lem.
Yes, please.
You are now basically assume that the kind of in QCD axions, this would be called that Pichet-Quinn symmetry is broken before inflation. So
Yeah.
your axion appears before inflation, and it is it makes a especially independent field initially in the whole
Yes.
universe.
Yeah, absolutely. Yeah.
Yeah. So this is the case. Okay. Thanks.
That's right. There's of course the possibility that the Pichet-Quinn is actually also broken only after inflation. In that case, you would get axion strings and so on. And I would actually comment on that. We'll come back to that in a moment. Yeah, but for the most part, we can just, for simplicity, keep in mind the scenario where Pichet-Quinn is broken actually before inflation. But we'll come back to what you asked about below. So there are, of course, a lot of interesting effects, astrophysical effects that one can focus on, some of which we have worked on, but some of which actually a large number in this a large number of speakers and participants in this conference have also worked on. And a lot of them have to do with this wave nature, particular interference. And I'm going to focus on some recent work that we have done on vortices. I don't think I would have time to talk about black hole hair. Maybe if we have time, I'll mention a little bit, but mostly I'll focus on vortices. If you think about what I told you earlier about the fluid description, at first you might be puzzled by why I even want to talk about vortices. Because in the fluid description, if you think about it, the velocity is pure gradient flow. And if it's pure gradient flow, there's no vorticity, right? The curl of velocity is 0. So you might wonder, why am I even talking about this? The fluid description, of course, actually, if you think about it, it actually breaks down precisely at the places where the density vanishes. Because if you have the wave function, the amplitude vanishes. In those places, the phase is actually not well defined. And those are precisely the places where you have the possibility of having vortices or vorticity. So that's the loophole that I invoke at the end here, rho equals 0. Now, at the moment, it sounds like just a curiosity, right? Because the picture we have in mind is the following, that I have these waves. In the early universe, they have small amplitude, 10 to the minus 5 fluctuations. As the universe evolved, gravity amplified these fluctuations so that the amplitude is now large enough that wave interference, because rho goes like psi squared, leads to the possibility that you could have this complete destructive interference, that the density is equal to 0. Naively, it might sound like this must be a very rare phenomenon. And what I want to show you, not right now, but maybe in 5–10 minutes, that in fact is not a rare phenomenon at all. In fact, it's very generic. But for the moment, let's just postpone the question. How often does it happen? How rare it is? Let's focus for now on the possibility that this could happen somewhere, and let's focus on what happens close to these regions where you have complete destructive interference. In about 5–10 minutes, I'll come back to a discussion of how often does this happen, okay? So I'm going to run a very simple argument. First of all, I'll do an argument that is not actually about vortices, it's more about domain walls, but it's easier to describe and is actually applied when you have one spatial dimension. So let's imagine you have this wave function and you have one spatial dimension. And let's imagine that at some point on the x-axis, that's why my spatial dimension, let's say at x equals 0, the origin, the wave function just happened to vanish. And again, the picture we have in mind is just to happen to vanish by chance due to disruptive interference, okay, chance interference. Because you have a superposition of waves with random phases, occasionally it could happen. So let's do a Taylor expansion. It's very simple. So I have psi of x It vanishes at the origin, so I can cross that out. The lowest order term in the Taylor expansion is just the first gradient of the wave function evaluated at the origin, multiplied by x, right? And then, of course, there could be higher order terms. Let's for now assume the first order term, the first gradient, does not vanish at the origin. Generically, that's the expectation. And what I'm going to describe is so, in some sense, so trivial that it might be easy to miss. So I'm going to go through it slowly. So please bear with me if this is too obvious to you in any case. So remember the wave function is a complex quantity. So here I'm plot the imaginary and the real part of the wave function. And imagine I go along the x-axis from x negative to x positive, crossing 0. The wave function, if you plot it properly, will move along this blue arrow. Yeah, this blue arrow basically represents the gradient, the first gradient of psi evaluated at the origin, right? The wave function will cross from somewhere here, crosses 0 and emerge on the other side. What is interesting is if you think about the wave, the phase of the wave function. The phase, of course, if you think about it, is obvious now that it has a pi jump as you cross the origin. So on the right, I actually plot the phase just to make that obvious. If I plot the phase as a function of x, it has a pi jump, and that is our candidate domain wall if you want. So that if you think about the phase, there's some special feature as x equals 0, and what you have is the kind of analog of what you might be familiar with, some kind of topological defect where the phase exhibit a jump in pi. And this argument can be extended to higher dimensions. And I'm not going to go through the argument in detail, but if you go beyond one spatial dimension, you basically would have vortices. If you want the equation that I just wrote down, you can just make x a vector now. Again, the 0 order term can be crossed out because we are interested in the neighborhood of a point where the wave function vanishes. The first gradient dominates, assuming it's non-vanishing. And if you run through the same argument that I actually told you earlier, what you have is not so much a pi jump. What you have is actually a winding of the phase. So imagine that you actually ask yourself, what are the set of points where the wave function could vanish? And here there is a very simple argument that tells you the set of points where the wave function could vanish in 3 spatial dimensions, it should form basically a line. And the argument is as follows. We are in 3 spatial dimensions and we want to demand both the real and the imaginary part of the wave function vanishes. If you think about just the real part for now, in 3 spatial dimensions, the set of points where the real part of the wave function take a certain value, for example, if it vanishes, it takes the form of a surface generically. The same is true for the imaginary part. And so the set of points where both the real and the imaginary part vanishes is the intersection of 2 surfaces, which is basically a line. So generically, when you have 3 spatial dimensions, the set of points where the wave function vanishes should basically be something like this purple line. And if you run the same argument that I presented before for the domain wall, if you can actually show the phase as you go around a loop around this line would have a non-trivial winding. And the winding would be by integers of 2 pi, as you might expect. And if you translate into fluid variables, it basically says the velocity integrated around a loop would goes like basically 2 pi n. N is an integer divided by m. M is basically the mass of the axion. And you can show that this n would be equal to 1 if this linear term does not vanish. You will have basically single winding. If by chance this linear term vanishes, then you have to go to a higher order in the Taylor expansion, then you would have higher winding. So all these arguments I'm not going through in detail, but it's fairly similar to this domain wall argument I gave earlier. Moreover, there are actually some very generic statements you can make about the density and velocity profile. If you think about this Taylor's expansion argument, the wave function is linear in X. So it's linear in separation from basically the vortex or where the wave function vanishes. Since the density is the wave function square, the density must go like the separation square. So that's the origin of this R square that I wrote down. When n is 1 single winding, then it's just R square. You could have higher winding if this first order term happens to vanish. So that's why I put an n here. But as I will show you actually a little bit later, what we find when you have a superposition of random waves with random phases, generically, you only have single winding, as you might expect. Generically, you don't expect the first gradient to vanish. So mostly we have rho goes like R squared. Similarly, you can also work out the velocity profile. It also can be seen basically from this circulation integral. On the right-hand side, this circulation doesn't actually depend on distance. So it tells you that velocity must drop like 1 over r. If the circle is bigger, the velocity goes like 1 over the size of the circle. So these are very generic prediction, just based on a very simple Taylor expansion argument around basically these topological defects, where you have the wave function just by chance, again, by chance vanishes. In the neighborhood of these points, the density goes like R squared, the velocity goes like 1 over r. And now let me come back to actually the question that Dima asked earlier. If you have Petri-Queen symmetry that occurs after inflation, of course, you can also have topological defects, but of a very different kind. It's not the same as the topological defects that I mentioned here. I just want to make that distinction just to make that completely clear, right? So a lot of you might be familiar with topological defects, which are often called axion strings. For axion strings, if you want the U1 that is associated with that topological defect is the U1 associated with Petri-Queen U1. That is different from the U1 that we are using here for these topological defects. The U1 we are using here in some sense is more mundane, is more ordinary. This is just the U1 associated with number conservation that you have in the non-relativistic regime. So these are very different from the axion string. So let's make sure we keep those things separate. And this, yeah.
Ask something different. I get that. Suppose Petri-Queen is broken after inflation, and yes. Suppose the actual axion strings, they vanish. They vanish with the main wall, etc. But people say, the simulators, they say that there is a mixture of axion waves from the very beginning going in the universe. Is it true that there are, from your viewpoint, there are many closed strings which cover all the universe from the very beginning in this case?
You mean closed strings of this kind, of like these vortices?
Yeah.
That would be true as long as the amplitude of the fluctuations for the axion wave is big enough so that you can have complete destructive interference.
Order 1, yeah.
Yeah, as long as it's order 1 or bigger, then yes, I would say so. Mm-hmm. And the point I want to emphasize is, even if it's not order 1 in the early universe, it is going to be order 1 in the late universe just because of gravitational instability. Mm-hmm. So the claim is this is inevitable once you go to a nonlinear regime inside halos, for example. This is going to be true either for QCD axions or for fuzzy dark matter. Basically, anything in the wave regime should exhibit this phenomenon. Yeah. And if you look at this slide, I actually have not used many assumptions even about the dynamics of the wave function, right? Because this is just a Taylor expansion argument. It's a very simple-minded argument. And now I want to convince you that these things actually form, right? Because so far, I assume these things are there, that the density actually vanish or the wave function actually vanish at certain locations. Next, I want to show that this is actually very generic. So this is what I want to show you next. This is one simulation of a cosmological simulation of fuzzy dark matter, where we start from small fluctuations, Gaussian initial condition from the early inverse, and go all the way to the nonlinear regime, and we actually zoom into one halo. And in this halo, here in the middle, this is one slice of the density. The color coding is density. Blue means basically low density. So this is a candidate axion ring, or I should not call it axion ring, sorry. Let me call it a vortex ring, just to differentiate from QCD axion strings. This is a vortex ring, at least it's a candidate. I call it a candidate ring because you should not believe me if I just show you this picture and claim that this is a vortex ring, because in a numerical simulation, the density can never be strictly zero anyway, right? It can be small, like here, the blue color coding means it's very small, but it's never strictly zero. So how am I sure this is an actual vortex ring? The way to make sure is actually to look at the phase. So instead of the density, you can also look at the phase. And if I flip this ring by 90 degrees and I check the phase, whether it winds around, if I see winding, then that would be a better evidence that actually I have a vortex ring. And before I show that to you, I should also emphasize, I should have said that earlier, these vortex structure, as I argue, in general, you expect the set of points where the wave function vanish should form a one-dimensional string. Of course, this string, we expect them not to end, and therefore they should close. And therefore, generically, what we should expect is actually a ring, a closed loop, like what Dima was asking earlier. So this is one candidate. In the next picture, I'll show you the phase.
I actually have a question.
Yes, Dima.
First, is it true that first you form small loops and then they grow?
Actually, that's a great question. That seems to be what happens. In fact, I'll show you a movie at some point how these things evolve. Yeah, but I believe so. I believe so. This is the phase. The color coding is the phase. It's not so easy to tell what's going on, but essentially in this picture, this point at where my pointer is, and this point are where that ring crosses the plane of this slide, basically. And you can check, basically, there is winding around the intersection of one side of the ring and an opposite winding on the other side of the ring. And this is how you can make sure that you are not just by mistake identifying just a low density fluctuation as a vortex ring. But once you know this is possible, you can actually devise an algorithm to systematically look for these things. And so I'm going to show you another simulation, which is like that. This is a simulation of a halo. I basically am not even showing you the actual density profile of the halo. I'm just highlighting the ring that you can see in this halo. Turns out this is very generic, and you can actually even quantify what is the number density of these topological defects. These number density turns out to be of the order of 1 per de Broglie volume. There's on average 1 vortex ring per de Broglie volume. That seems to be the statistical expectation. And this is an example where the ring can be very easily seen, and they are nice. They are almost circularly symmetric. But this is an artifact of the fact that this halo has very symmetric initial conditions. This is a halo that formed from essentially spherical collapse. If I look at a more realistic halo, it would look more like the next picture. So they are more messy, these rings. They're actually not circular in shape. You can also see there are many sizes.
What is the typical size of the string?
I will show you actually maybe in a few slides the size distribution. You can actually measure the size distribution. They have all possible sizes going from very small all the way to about the de Broglie wavelength size. Beyond the de Broglie wavelength size, there are very few that are bigger. It becomes exponentially suppressed. I will show you the distribution. So sorry. So we did a few checks. So let me go through some check, right? Because I show you by the Taylor expansion argument, the density around these vortex rings should go like R squared. So we can check that. This is basically a few vortices. We plot the density as a function of separation from the vortex. And indeed, approximately, it goes like distance square. We can also plot the velocity profile. The velocity profile does drop like 1/r as you expect, but it deviates when you go sufficiently large, which is also what you expect, because it only has this universal profile when you are sufficiently close to the vortices. And let me also just show you some very simple analytic solutions that have vortices. Because these simulations, we can run them, we can show them that they form, but to get intuition, it's always useful to have some analytic solutions. And if you think, actually, you don't have to think very long to realize, in fact, there are extremely simple solutions you can write down. So let me just show you a few. If you remember, you have the Schrödinger equation. Let me turn off gravity, because in that case, you have a linear equation. You can write down the solutions immediately. The simplest solution that have a vortex is actually this one. This is just a static solution, right? Linear in X and Y, forget about Z, let's say 2-dimension, right? Or this describes basically a vortex string, basically extending along the Z direction. If you think about this, this clearly solves the Schrödinger equation because it's static, no time derivative, and of course it's annihilated by second gradient. But this solution, if you look at the phase, clearly it winds around, right? It's easy to see. And the wave function vanishes at x equals y equals 0, which is basically along the z-axis. So this is the simplest possible solution that illustrates a vortex, basically a vortex string. Of course, you can write down more non-trivial solutions, which I'm not going to go through here. You can write down solutions that describe a vortex ring that actually moves. In fact, if you study this solution, you can actually see the motion of the vortex ring is correlated with the size of the ring. The smaller ring actually moves the fastest. The bigger ring actually moves the slowest. It correlates with 1 over the size. This actually is related to what Dima was asking. This solution actually corresponds to a vortex ring that nucleates at some particular time, starting from 0 size, and then it grows to be very big, and then it shrinks and then disappear. And this solution also emphasizes one point, which is I should have said earlier. These topological defects, they are very fragile, unlike more familiar topological defects. These vortex rings, they can appear and disappear. They can come and go. And from the interference point of view, it's not surprising because these things form just because by chance you have disruptive interference. You form them, and this interference pattern change over time anyway because it's dynamical. And so it's not surprising these defects can actually form and disappear. And the way they seem to form and disappear is kind of like these solutions. You nucleate a very small ring, it can grow, and then it can shrink back and then disappear. And you can even look for solutions where these vortex rings, they cross, and ask what happened when they cross. So there's a lot that you can deduce by just studying these very simple solutions. And let me show you a simple picture of how to think about the motion of these rings. Here, I show you one ring. The velocity circulation goes like this, and correlated with this circulation, there is an overall bulk motion of the ring that goes in this direction. And once again, you can show the bulk motion of the ring is inversely proportional to the size of the ring. Once you know these things are possible, in fact, the easiest way to generate them is to even just forget about gravity. Imagine you just write down a code that generates basically a superposition of waves with random phases, much like what Dima does in his kinetic model. You generate them. This is a 2D example. Let me say I do it in 2D. I have a superposition of waves with random phases, and the waves have some spread in momenta, let's say. And then if you plot the phase on the left, you can see there are these points which are highlighted in red and blue, where the phase actually winds around, have non-trivial winding. These are the location of basically what are vortex points in 2D. In 2D, there are vortex points. In 3D, it would be like vortex ring. And of course, if you plot the density, these are also precisely the location where the density is very low. That's why they are highlighted in blue. And these things are very generic. And in fact, from this point of view, since these are simulations strictly without gravity, you just have a superposition of waves with random phases. You can even calculate analytically what is the generic prediction for the number density of this defect. And indeed, you will get one per the Broglie area in 2D or the Broglie volume in 3D. So you can even show this analytically. And it confirms what we see in these simulations with gravity. Let me show you a movie. This is a movie of an analytic solution where you see these strings moving around, nucleating and crossing, just to give you an idea. The two surfaces are the surfaces of vanishing real and imaginary part of the wave function. So you can see these rings are actually very dynamical, and this is just one particular simple analytic solution that you can write down, just to show you what could happen. So some additional comments. The first comment, I think I essentially covered that already. Naively, you might think this defect should be rare because this is complete destructive interference. But in fact, you can actually show that these are not rare at all. It's very generic. You have roughly one vortex ring per de Broglie body. And we check this both in simulations with gravity, and we check it by just computing analytically for a model where you have just a superposition of waves with random phases. Small rings move faster. It goes like 1/r. Or if you want, if you have a big ring, but it has certain segments that are very curved, those segments also move faster, essentially. There is a very interesting question about angular momentum. I think I'm maybe running out of time. If you are interested in the connection with angular momentum, maybe we'll come back to that. The zero order answer is, in fact, these vortices do not seem to have a whole lot to do with angular momentum, but we can come back to that with questions and answers if you are interested, okay? And what else can I say? This is the number density of vortex rings as a function of sizes. This is the question that Dima had earlier. So we can measure the number, the distribution of ring sizes, basically. The x-axis is the sizes. This is basically the number. The distribution is actually well fitted by an exponential, if you can see. The exponential has a one characteristic scale, and the scale is nothing other than the de Broglie scale, right? So basically it tells you beyond the de Broglie scale is exponentially suppressed. But once you go below, the de Broglie scale seems to be more or less flat. You have a flat distribution of strings of sizes from 0 size up to the de Broglie scale. Roughly speaking, that's what's going on. And one interesting thing we can also measure from the simulations with gravity is the one-point distribution of the wave function psi. Or you can think of this as the one-point distribution of the density. Yeah. So this the wave function normalized in some way. This is the probability distribution, is the solid line. Now, if you think about the solid line, the fact that it actually peaked at 0, it tells you basically there is disruptive interference going on, meaning this probability distribution has non-trivial contribution all the way to when the wave function amplitude goes to 0. That is the phenomenon of disruptive interference. And there is also this long tail. These are basically the constructive interference, if you want. There is a model coming from just pure superposition of waves with random phases. If you use that model, you can actually deduce what is the analytic expectation for this probability, and this basically this Gaussian, which is basically this dashed line. So this describes reasonably well for disruptive interference at the basically low density or low wave function amplitude end of the probability. It does not describe very well what happens when you have constructive interference, or actually what is going on. You could also interpret this in normal CDM, you might even call this subhalos. This might be, some of them are even subhalos in these simulations. I want to show this because the fact that this distribution is there affect interpretation, not just for fuzzy dark matter, but for even QCD axion. And in fact, it was emphasized by this nice paper last year by Gary Sanders. And Gary is one of the speakers at the conference, so he might even talk about it. So I thought I should show it. And he and collaborator emphasized the fact that there's this distribution affects interpretation of QCD detection, axion detection experiments. And that is an important point. And perhaps this figure actually shows that in terms of thinking about the implication for experiment, we might even have to think about the fact that the distribution has this long tail, which is not captured by this random phase model. And by the way, this random phase model was also the same model that Gary Sanders used in that discussion and collaborators used in that discussion. Okay. And I think this is all I'm going to say about kind of studying this, the density, velocity around these vortices and their statistical distribution and abundance. In the rest of the time, I think I'm probably running out of time already. I'll very briefly mention the observational and the experimental implication. I'll try to be quick there. But just let me just pause here in case Dima have any questions.
Well, I have a couple of questions.
Yeah.
Yeah, so general question. First of all, when you calculate this one-point distribution, what is the ensemble that you are using? What are you averaging of? Volume or some ensemble? Yeah,
it's just volume. So from the gravity simulation, it's really just volume. So we have a halo that formed from these kind of random initial conditions, and then we just measure averaging by volume what is the one-point probability distribution. Yeah.
Mm-hmm. And also I have very general question about the string axions, okay? So
Yes.
that's more or less the starting transparency.
Yeah.
And it's well known that the mass of the string axions is proportional to the exponent, which comes from the non-perturbative effects. And
Yeah.
some people say that, okay, since this is an exponent, we should have every one axion per decade of mass. Okay, so there should be many axions. Was with mass 10 to minus 22. Second one is 10 to minus 21, and etc. So how do you think about how robust is the prediction? Can there be one axion, or there should be many?
Yeah, that's a very good question. I think it is very plausible if you look at this string theory construction that if there were one light axion, then why not multiple light axions, like what you said? I think it's very plausible. I don't see why not. I mean, so far we focus on one single mass just from simplicity, but I think it's very interesting to study these cases where there are multiple light particles. And in fact, there have been some papers on that. Yeah.
Mm-hmm. But there could be one, right? It's not closed by the string theory. It's not. It's an open possibility that there is.
Yes. Yes.
Okay.
I agree. I agree. Yes.
Thanks.
I mean, even for the fuzzy dark matter, 10 to the minus 22 electron volt, already, if you also believe there is the solution to the strong CP problem, that 10 to the minus 22 cannot be the QCD axion, so there must be another light particle, which is the QCD axion. Okay. So already there, you need two light particles already. Yeah.
Yes. Yeah.
Whether they both contribute significantly to dark matter, that depends on the precise model. Yeah.
Okay.
Yeah, okay. But it's very plausible.
Okay.
Thanks for asking. So I'm going to close with some just thoughts very quickly about observational and experimental implications. Now, for observational, and by observational I mean astrophysics signatures. In that case, for astrophysics signatures, you really need to focus on the ultralight regime, because if the dark matter particle is not super light, like 10 to the minus 22, or at most, let's say 10 to the minus 20, then it's not so easy to come up with observational signatures in astrophysics, unless you are thinking about kind of exotic compact objects. That kind of is a separate category. In that case, then yes, you can even consider axion that's not ultralight. But for the most part, for what I mean by observational signatures, I'm going to focus on the ultralight regime. And one possible signature, for example, is gravitational lensing, right? Because what we have in mind now is a halo with a lot of substructure because of interference. Yeah, some of this substructure is vortices, vortex rings, but they don't even have to be. There are all kinds of substructure. And you can ask yourself, well, what would gravitational lensing by a vortex or vortex string or vortex ring look like? If you have a distant star and you have a ring or a part of a ring kind of scanning over along the line of sight between you, the observer, and that star, it would cause that star to actually have a displacement. The displacement is very small. You can actually work it out. If this is if you assume 10 to the minus 22 electron volt and so on for the dark matter particle, you get 10 to the minus 4 arcsecond displacement. 10 to the minus 4 arcsecond sounds small, but actually it's not so small that it cannot be measured. In fact, Gaia can measure actually better than that in principle. Unfortunately, if you work out how long does it take to have that 10 to the minus 4 arcsecond, it takes a very long time, 10 to the 5 years, which means per year, the displacement is just too small for it to be measured by an experiment like Gaia. There are discussions in the literature by, for example, this set of authors who look at the collective effects, basically not just from just one star, but if you have a vortex ring or some interference substructure of some kind, or even CDM subhalos, which is what they focus on. And it's gravitational lensing, not just one star, but a whole bunch of stars. Let's say you have many, then maybe by the collective effect of all of them, you can pick out the noise and see very small effects. So that's what they propose, and you're welcome to take a look at that paper.
How do you differentiate this displacement from the peculiar motions?
Very good. In fact, I think that is going to be the major source of noise. In fact, because as you correctly point out, the stars, they also have peculiar motion. They move. So how do I tell them apart? I think what this set of authors have in mind is something like this. They say, if I have some substructure, I think what they have in mind is a CDM subhalo, and it lends a collection of stars. It will cause the stars to move with a very particular pattern in some correlated way. And maybe that way you can tell them apart from some just random peculiar motion. That's what they propose. But you are absolutely right. The peculiar motion, in fact, is a large effect. In fact, in some cases, it's actually a lot larger than this effect. So you have to be careful. That's a good point. The one situation in which we find that there might be observable effect, meaning observable even that already exists in the data, is in a different situation, is again gravitational lensing, but is actually gravitational lensing in a very different regime. So what I show you, I put out this picture, is from this paper by Lang Dai and collaborators. And it's a strong lensing system. And for example, I'm just going to focus on these two images. You see these two images? This is basically a background galaxy or part of a galaxy strongly lensed by a foreground galaxy cluster. The magnification is very extreme. It reaches of the order of 100. So huge magnification, meaning these two images are very close to the critical line. The critical line is where formally the magnification diverges, at least formally. And you can show, based on, again, very simple Taylor expansion argument, when you have two strongly magnified images, when they are very close to the critical line, in fact, generically, you expect the magnification of each should be equal. They should differ by actually a fraction of actually 1%. So they should be actually fairly close to being equal. What is observed in this particular system, however, you can almost see by eye, these two images do not look like they have equal magnification. It looks like maybe one of them is just slightly more magnified than the other. In fact, they can measure it, and the difference in magnification is at the level of 10%. And then the question becomes, how do you explain it? One way to explain it, which they also discuss, is that the gravitational potential caused by the cluster and the foreground galaxy is not completely smooth, that there is substructure. It's important the substructure has to be on the scale of the image separation or smaller, so that it affects one image but not another and causes the difference in magnification. And in their paper, they consider substructure due to CDM subhalos. And that seems to be sufficient to give you this 10% effect. What we estimated is, how about just this interference substructure due to fuzzy diameter? Can that give you also 10% effect? And it looks like it is possible also. So you can have some form of kind of detection of interference substructure by this kind of effect, gravitational lensing effect. Of course, then the challenge becomes, how do you differentiate this different interpretation? And if we have more system of this kind where the image separation have different kind of angular separation, you should be able to measure how the substructure vary as a function of scale, and that should give you some idea what is the substructure behind. Is it consistent with this interference substructure or is something else? Okay. And then there's the heating of tidal stream, which I'm not going to go into now. I think it's discussed in a talk by Anna Bonacca, which you will hear in this conference. I'm going way over time, so I'm going to skip everything about black hole hair. Sorry about that. I'm going to end with this slide just to have a few words about experimental implication. And here I focus on actually something like QCD axion. So here, the dark matter is light, but does not have to be ultralight. So not necessarily fuzzy dark matter, QCD axion. And I focus on the kind of coupling that is very often discussed for the QCD axion. For example, the coupling, like what Dima discussed, is coupled to FF dual, or if you want E dot B of the photon, or a derivative coupling to fermion. The fermion could be quarks, for example, nucleons, or even leptons. And they are both suppressed by the axion decay constants, this little f here. And I'm not going to go over all these experiments. Essentially, they are experiments that make use of the coupling to photons. Basically, the first, there's a whole bunch of them. The most well-known one is probably this microwave cavity experiment, ADMX. There are, of course, experiments that relies on coupling to the spin. For example, Casper and other experiments. What I want to emphasize is these actually experiments, they are all measuring slightly different things associated with the axion. It could be the amplitude of the axion oscillation. It could be the time derivative. It could be actually the spatial or temporal variation. It could be gradient and so on. They are all measuring slightly different things. And here I want to kind of just explore, just very briefly, what happens if in the halo, the Milky Way halo, in particular the solar neighborhood, the dark matter field is in fact highly inhomogeneous due to this wave interference. What does that mean for these detection experiments? So these phi should be thought of now as it oscillates in time, of course, like what axion should do, but in fact, it should have non-trivial interference pattern, spatial and time variation. In particular, we are interested in non-relativistic regime. So there's this wave function, which vary with time slowly. And then there is this fast oscillation on time scale of the mass of the axion M. In other words, if I pick a location where the dark matter detector is, and I think about what happens as a function of time, this is probably what it should look like. There should be fast oscillation time scale of the order 1/m. I picked 10 to the minus 9 seconds for m, which is 10 to the minus 6 electron volt. There should be actually longer time scale modulation, which is essentially, if you want, the de Broglie time, is the de Broglie wavelength divided by the velocity dispersion of the Milky Way or the solar neighborhood, which is on a longer time scale. This picture is emphasized in a number of papers by these authors. And they have explored some of the consequences of having basically essentially this kind of interference pattern, if you want, that should really go through your detector. I just want to leave you with just a few thoughts, based on this picture of having dark matter waves for dark matter detection. Number one, I think it's perhaps useful to emphasize that because of this stochastic phenomenon of having waves with random phases, it's probably useful to think in terms of measuring correlation functions, because what you should have is correlation stochastic fluctuation in psi or phi, which is what you measure in this axion detection experiment. For example, you can think about two-point function in the density, which is like two-point function in phi square, two-point function in time. And you can show on long time scale, long time separation T and T prime, it has this characteristic tail. This is maybe give you some additional feature to look for when you are analyzing data that's noisy. Second point I want to make, which is sort of interesting, for vortices, of course, those are places phi actually vanishes, right? So for some of this experiment, at the location of vortex, the signal actually goes to 0. But for some of these other experiments, because they are sensitive to gradient of phi, even at the vortex, the signal actually does not vanish. So exactly what signal you see in different different kind of detection experiment is different when you encounter a vortex. One last thought, I don't have actually a very concrete suggestion, but here maybe there is something interesting about the phase, because if you think about it, the vortex is interesting basically in terms of the winding of the phase. And the phase, if I write in terms of real axion field, is essentially the phase here that shows up in the phase of these rapid oscillations. And basically what we are saying is there's interesting spatial structure in this phase when you have vortex rings passing through your detector region. And maybe that is something that we should think about, because in most of these detection experiments, most of the focus is on measuring this amplitude, which is of course the interesting thing because it tells us the dark matter abundance. But perhaps there's something interesting about the phase that we can think about. And I have to confess, I'm being a little bit vague here. What should we focus on? And I actually would welcome very much ideas about that. And I think I'll just close with this slide that kind of summarizes what I have talked about. And I've gone way over time. I thank you for your attention.
Thank you, Lam, for the wonderful talk.
Thank you.
So it was very good and understandable, at least to me. So let me stop the record.
Okay.
Very much.